Hello people, look, we have an applet here. There's a gas chamber and these are all the Godzillion number of gas particles. There's a pressure gauge and there's even a thermometer. Now there's a slide bar here that I think I'm supposed to slide. Okay, we are heating the gas up. Do you see the temperature go up? So I guess we can also cool the gas down. Those are the ice cubes. So that will slow down the motion of the gas particles. There's also a handle here. I wonder what will happen if I push it in. What? Do you see? Do you notice that the temperature go up? Which means if I move the handle the other way, the opposite should happen, right? Yep, see, the gas is cooling down. So let's try it again. Now let me push the handle in. Wow, see? The temperature went up. So the temperature is 266 Kelvin now. If I pull it out now, it's supposed to cool down. Yep, see the temperature cooling down? So what's happening, man? Now if you ask a primary school student how we can make things hotter, they'll say, oh, give it some heat. Heat energy. Then how can you make it colder? Oh, take away some heat. But what I've shown you just now using the applet is there's another way to change the temperature of something. So if it's a gas, if you compress the gas, it becomes hotter. On the other hand, if you allow the gas to expand, then it becomes cooler. How does that work? Now, microscopically speaking, the piston compared to the gas particle will have a very, very large mass. So when each gas particle collides with the piston, it's like a collision between a tiny mass and a humongous mass. If the piston is stationary, what do you think is the outcome of such a collision? So after the collision, the gas particle will rebound with the same speed that it collides into the piston with, right? Remember, we assume that in an ideal gas, all the collisions are elastic, meaning the total Ke should remain constant after the collision. So if the piston is stationary, then you can have all the collisions, but the average Ke of the gas particles should remain constant. What if the piston is moving this way with a speed u? Then what is the outcome of such a collision? Now remember, we assume that the collisions are elastic, so we can use the relative speed of approach equals to the relative speed of separation. So if you do this minus that is equals to that minus this, you can show that after the collision, the gas particle will rebound with a speed of v plus 2u. Now meaning after each collision, the gas particle gains some speed. So if you have Godzillion number of collisions happening and every gas particle is gaining Ke after the collisions, then you can see why the average Ke of the gas particles goes up. That results in a hotter gas. On the other hand, if the piston is moving away from the collision, then you can solve again using the relative speeds of approach and separation, that after the collision, the gas particle will be moving at a slower speed of v minus 2u. This means that after each collision, the gas particle loses Ke. So as a gas, the average Ke of the gas particles decreases, which means that the gas has cooled down. So this gives a microscopic explanation for how the temperature of a gas can be affected by its compression or expansion. But can we have a macroscopic explanation? Yes, we can. So we have here a gas at pressure P. Now if you want to compress the gas, you need to apply an external force. And if you do manage to compress the gas by moving the piston a distance of delta S, then we can calculate the work done by this force. Remember, work done is force times the displacement. If the cross-sectional area of the piston is A, then we can write the external force to be P times A. Remember, the external force is required in order to overcome the pressure force exerted by the gas. So the magnitude of the external force required is simply P times A. If we group the A and the delta S together, we can write it as P times delta V. So who is delta V? Delta V is the change in volume. I stick a negative sign here because we're actually looking at the decrease in volume of the gas. We can see the compression of a gas as doing work on the gas. And where does this work done go to? It goes into the internal energy of the gas. So in a nutshell, we can affect the temperature of a gas by doing work on it. And the amount of work done can be calculated by the pressure times the change in volume of the gas. So if you have a stationary piston, then there's no change in volume of the gas, right? Which means there's no work done on the gas. Since there's no work done, the internal energy of the gas stays constant and the temperature stays constant. If you're compressing the gas, then we say that we are doing work on the gas. You can think of it as the surrounding doing some positive work on the gas. This will increase the internal energy of the gas, which translates to a higher temperature. On the other hand, if you allow the gas to expand, then the work done on the gas is negative. Or another way of looking at the same thing is to say that the gas is now doing work. So the work done by the gas is positive. But where does the gas get the energy from to do this work? From its internal energy, of course. That's why when a gas expands, its internal energy decreases, which is how its temperature can drop. Okay, I think what is important for you to learn from this video is there are two ways to change the temperature of your system. The first way, called heat, is the one that's familiar to everybody. If you want your system to gain heat or lose heat, it has to be colder or hotter than the surrounding, which means a temperature gradient is required. If you have to do calculations, you do the MC delta theta and M times latent heat. So heating is familiar to everybody. Work is the one that's new to you probably. It turns out you can make your gas hotter just by compressing it. It can also cool itself down by expanding. If you have to do calculations, it'll be pressure times the change in volume. So why didn't we teach you this last time? It's because last time you were studying liquids and solids only. And the volumes of liquids and solids usually do not change much, meaning it's very hard to compress or let it expand. So the delta V used to be 0 for all the calculations that we have made you do last time. But now we are studying mainly gases, and gases are highly compressible. So you must not ignore the work now. Get it? Alright, ta-ta!